Welcome to Pharma Drama, the channel where we look at the science of medicines. Today we're going to look at a physical property of liquids, one that I know confuses a lot of you: surface tension. We'll look at the definition, what causes it, and what effect it has on liquids. So, if you're experiencing tension, relax. Everything is better with a hot beverage. And let's dive in. You've probably seen the effects of surface tension more than you've thought about what it is. It's why water falls as droplets, liquids spontaneously rise in capillaries, soap bubbles form perfect spheres, and objects can float on water without getting wet. It also affects how liquids spread on solid surfaces and how they behave in things like inkjet printers. So, all in all, quite important. Surface tension is most easily explained by thinking about the forces between molecules in a liquid. I shall assume water, but of course the principles apply to all liquids, and we'll look at some other examples in a bit. Water molecules are very good at forming hydrogen bonds, so there are reasonably strong attractive forces holding them together. Two water molecules will therefore be held quite strongly together. But of course, there aren't just two water molecules in a volume of liquid, say in a beaker. There are trillions, and they are all moving about randomly. This means that if you were a water molecule in the middle of the beaker, you would be surrounded by many water molecules in all directions, and you would be attracted to all of them. The effect of this, then, is that in the middle of a volume of water, we call this in bulk solution, there is no net attractive force acting on any particular molecule. The water molecules are all attracting each other, but because they are all around, each molecule feels small forces in all directions. Now, let's consider the molecules located right at the surface of our water in a beaker. Below them, and to their left and right, there will be water molecules, which they are attracted to. Above them, however, and assuming our beaker of water is in air, will be molecules of gas, primarily nitrogen, but also oxygen. Being a gas, the molecules in air are way more separated than those in a liquid, and are moving with much greater energy. So there are only very few molecules above our water at the surface. Thus, even if our water molecules at the surface could form attractive interactions with the gas molecules, any interactions would be weak and very short-lived. The effect of this is that the water molecules at the surface will be strongly attracted to other water molecules around and below them, but will have virtually no attraction to the molecules of gas above. Overall then, they will feel a net attraction laterally, that is, a pull across the surface, and from below. And it is these attractions that lead to the surface of water acting like a film, and this is what we call surface tension. The surface tension of water is relatively high, so this surface film is strong. This is why insects and leaves are able to float on the surface of water. The downwards force they exert under gravity is less than the surface tension. This is not true, by the way, for shopping trolleys, which is why they sink when thrown into canals. How do we quantify the magnitude of surface tension? Because the value will clearly vary for different liquids. There are two ways in which the units of surface tension can be defined: force per unit length or energy per unit area. They are equivalent, but I know a lot of students find units like these confusing. So let's look at where they come from in a bit more detail. Let's start with force per unit length. Imagine the surface of our liquid held in a beaker. If we drew an imaginary line of any length L on the surface, we can think about what forces are being exerted on the line. Since there is a tension, which is a pulling force, there will be a force, let's call it F, pulling the line to the left, and a similar force pulling the line to the right. In effect, the line won't move because the forces acting upon it from each side are equal. Overall then, we can quantify surface tension, which we give the symbol gamma, as force divided by 2 times length. 2 times length because there is a force acting on both the left and the right side of the line. Force has units of newtons and length has units of meters. So overall, surface tension has units of newtons per meter. There is another way to think of surfaces, and that is to think of what happens when we create a new surface. I find it easier to consider this for solids, so I will. But the same principles apply to liquids. Imagine we have a block of some material, A. It has a surface already, but if we want to make an additional surface, we can do so by cutting it in half with a knife. To do that, we would have to apply work, or energy, to the knife to cut through the material. If the material was soft, like butter, the amount of energy would be quite low. But if it were hard, like steel, we would have to apply a lot of energy. Clearly then, different materials require different amounts of energy to cut them. After cutting, we now have 2 blocks of material A, and if we look at the total surface, we will see we have created 2 new surfaces, 1 on each block. What this means then is that we have added energy to our material, and in so doing, we have created some new surfaces. This means that the energy we have added must be associated with the new surfaces, or creation of a surface requires energy. This energy is called the surface energy for this reason, and is equal to the work added in joules divided by the surface area created in meters squared. The situation is exactly the same for liquids. Energy must be added to create a surface. The difference is that in liquids, the molecules are more mobile than they are in solids. So another way of looking at this is to imagine that water molecules would prefer to be in the bulk of the liquid, no net force, and to get them to be at the surface, unfavourable, requires them to be given extra energy. That extra energy is tied up in the surface tension. I hope that makes sense. The take-home point is that creation of a surface always requires an input of energy. And that means that surfaces are energetically unfavourable. Because of this, where possible, a material will always act to minimise its surface area. One key difference between solids and liquids is that the molecules in a liquid can move relatively quickly, so can change shape when energy is added. This is why soap bubbles form spheres and water breaks into droplets when falling. A sphere is the geometric shape that minimises surface area to volume. If you add energy to a solid to create a new surface, it can't change its shape to minimise its surface area, and so its surface energy will be high. When like molecules interact, such as water interacting with water, we call that the work of cohesion. And when dissimilar molecules interact, such as water molecules with the atoms in the glass beaker, we call that the work of adhesion. Surface tension is therefore a result of the work of cohesion. I mention this because how liquids behave when in contact with other materials will depend on the relative strengths of the work of adhesion and cohesion. Consider water in a small glass tube. At the edge of the tube, there is an interface between water and glass. The work of adhesion between water and glass happens to be quite high. So there is a strong pull for water molecules to spread over the glass. However, the work of cohesion of water is also quite high. So water molecules spreading over the glass drag more water molecules with them. The net effect of this is that water appears to creep up the side of the glass, and we see a concave meniscus at the surface of the water. This effect is what leads to the phenomenon of capillary action. If we widen the glass container, the work of adhesion remains the same, so the curvature at the edge of the water-glass interface also remains the same. But in the middle of the liquid, cohesion dominates and we see a flat surface, under tension of course. The effect of capillary action disappears. We could of course turn our glass tube upside down. Now gravity acts to pull the liquid down and out of the tube. However, in a narrow tube, the work of adhesion again means that water molecules are happy to spread over the glass, bringing other water molecules with them. And the water doesn't fall out of the tube. We instead see a convex meniscus. As we widen the tube, as before, the work of cohesion begins to dominate, flattening out the surface. Now though, the surface tension is not high enough to resist the force of gravity, and water falls out of the tube. Although again, surface tension causes the water to break into discrete droplets. These effects of surface tension and capillary action can be problematic in some applications. For instance, an inkjet printer cartridge consists of a number of very fine capillaries through which ink droplets are ejected. I think you might imagine that water-based inks can be quite hard to eject because of their high surface tensions. The ratio of adhesion to cohesion differs for different materials. For ethanol, the forces almost balance when held in glass, which is why almost no meniscus is seen in an alcohol thermometer. It also means ethanol has almost no capillary action, and were you to hold ethanol upside down in a capillary, it will simply drip out. For mercury, cohesion is much stronger than adhesion to glass, and so in a mercury thermometer we see a convex meniscus as the atoms in the mercury try to push away from the glass. Incidentally, the balance between adhesion and cohesion is what defines how a liquid spreads on a solid surface. When it rains on a freshly waxed car, you see lots of small water droplets on the surface. This is because the work of adhesion between water and wax is very low. Cohesion dominates and causes the water to form small spheres, as this minimises the contact area, exactly the same as mercury on glass. As the surface of the car becomes dirty or wax is lost, the work of adhesion increases and water spreads more readily. Measuring the angle formed between droplets of a liquid on a surface is in fact a measure of how they interact and spread, and this is called contact angle measurement. There are a couple more points we should mention. One relates to the downwards or inwards pull felt by molecules at the surface. This is analogous to a pressure, and indeed you could think of the interface between a liquid and a gas as being two regions of different pressure acting against each other. If the two pressures are equal, then there is no net effect on the surface and it will appear flat. The molecules on the surface will only experience a lateral tension. However, in the more likely case that the pressures are not equal, the surface will curve in order that the two pressures balance. The pressure experienced by water is called the surface pressure. Usually, the inwards pressure experienced by molecules of water is greater than the inwards pressure experienced by molecules in air. And the net effect is the surface of water will have to curve inwards in order for there to be equilibrium at the interface. The effect of the curvature is calculated by the Young-Laplace equation, where delta P is the difference in pressure on the two sides of the interface, gamma is the surface energy, and Rx and Ry are the radii of the curvatures in the x and y directions respectively. You can see from this equation that when the radii of curvatures approach zero, that is, when the surface becomes flat, delta P approaches zero, so that all makes sense. This effect gets larger as the volume of water reduces, because as the volume reduces, the number of molecules reduces, and so the fraction of molecules experiencing a net force increases. While the surface pressure is quite small for relatively large water droplets, it becomes considerable as the droplet size reduces. The final point is what happens to surface tension when we add molecules to water that like to be at the surface. Things like surfactants, for instance. We'll talk more about these in another video, but in brief, surfactants are molecules that are hydrophilic, or water-loving, at one end, and hydrophobic, or water-hating, at the other. Molecules like this don't want to be in bulk solution. Rather, they want to get their hydrophobic ends as far away from water as possible. And they do this by aligning vertically at the surface of water. This has the effect of dramatically lowering the surface tension and is what leads to surfactants helping water and oil to mix. But as I said, we'll look at that again in more detail in a separate video. For now though, I think that's the basics of surface tension covered. Remember that surface tension arises because at the interface between a liquid and a gas, there will be a net attractive force of cohesion on molecules at the surface laterally and from below. This causes a taut film to form at the surface. The magnitude of the force is defined as the surface tension, and it can be quantified in units of force per length or energy per unit area. Since energy must be added to create a surface, surfaces are energetically unfavourable, and liquids will always change shape such that their surface area is minimised. This is what causes droplets to form. When a liquid interacts with a solid surface, there are forces of adhesion. The relative strength of the forces of adhesion and cohesion define how the liquid spreads on that surface. We can reduce surface tension by adding surfactants. Okay, I hope you are now experiencing less tension about surface tension. Let me know in the comments. And if you found the video useful, please hit the like button and consider subscribing, as that really helps the channel. Otherwise, thanks so much for watching, and I'll see you again soon.